Welcome everyone. Today we are going to look at the tutorial on linear regression, linear discriminant analysis, and logistic regression. So we are going to look at the assumptions of linear regression, how to fit a linear regression in R, and we are going to be using packages that are within some of the data sets that are within some of the packages that we are going to be using. So let's start off by running this cell. You see the first code is to clear our environment. The second code is to set our working directory, and I've loaded some of the common libraries that we shall be using. So the second thing, we are going to use data from MAS and ISLR. If you don't have these packages, you can use these two commands here to install them. But let's go ahead and load that data. So MAS comes with the Boston dataset. So that Boston dataset has, I have included it as a data frame in our environment, as you can see. So it has these variables, scream, ZN, Indus. We shall see what this means. So this code attach Boston, it brings out all it makes R to be working with that data set that you have attached at that time. So let's look at the structure and the information about the Boston dataset that we are going to be using. So when you look in the help this side, you'll see that this is housing values in suburbs of Boston. The dataset is in a data frame that has 506 rows and 14 columns. CRIM means per capita crime rate by town. ZN is the proportion of residential land zoned over lots over 2,500 square foot. Indus is a proportion of non-retail business acres per town. So you see these are the age is the proportion of owned occupied units built in prior to 1940. So this is the data set that we're going to use, and we shall be using MEDV as the median value of owner-occupied homes in thousands of dollars. This is going to be our outcome for this analysis. We shall use this as our outcome. Else stat is the lower status of population percentage. When we look at a variable like let's see, yeah, if we look at a variable like Charles, which is Charles River dummy variable, meaning 1 if track bounds river, 0 otherwise. It is a categorical variable, so we have to make sure that it is a factor variable in our data set. So this is why we looked at the structure of the data set, which is structure Boston. And we see most of them are numerics, and chars, which is indicated as a categorical variable, it is being indicated as an integer. So we have to convert it to factor. This is what the next code is all about. So when we convert this as a factor, we see that it has now been looked at as factor with two levels, 1 and 0. So let's look for any missingness. If there is any missingness in this data set, this is all trying to prepare and clean our data set for use. So there are no missingness. There is no missingness. There are no missing values in this Boston data set. So let's try to look at simple summary statistics by running this command of summary. So we see that for numerical variables and integers, we are getting the mean, the first quartile, median, mean, third quartile, and the maximum. So that's how the summary is done. While for categorical variable like chars, it is giving us numbers 1, 35, and 0, 471. So by looking through this, you can you can get a rough idea of what these variables are or what the data set is. So let's start off with linear regression. We saw linear regression in our previous video. If you didn't watch it, you can watch the introduction to linear regression, the theory. So while preparing our linear regression analysis, we have to take into account of the assumptions of linear regression. First of all, we want to take out one of the assumptions is that these variables or the predictors are not correlated, or they don't have they are not highly correlated among themselves. So to determine that, we are going to run a correlation matrix. And to get a correlation matrix, I had to get out how to separate the numerical variables, hence writing this code, taking out the numerical variables, and select if this is a dplyr command, this pipe, select if is numeric. So for numeric variables, I again removed our outcome. Though it would be good to leave it there, I'll tell you why later on. But for now, let's remove it. Then run a correlation matrix. You can use the colors or you can use the numbers. This last code includes the numbers within the correlation matrix, and 0.7 is the size of the values or the font size. So let's run this. So running this, this is the first code for the plot where the method is on my color. So the colors indicate blue indicates high correlation. That's why its diagonal is all blue. While this is brown, indicates the very low or very high negative correlations. So this is like a heat map. While if you want to look at the real figures, you can use the second method as number, and you can change the font size of the numbers. As you can see, we have very many highly correlated variables, and by rule of the thumb, normally we take those correlations that are below 0.7 or below 0.6. It depends. You don't want highly correlated variables within your linear regression or logistic regression. Normally these G and GLM, generalized linear models. So except for longitudinal data. So I'm looking at Indus and this 0.71. These are highly correlated. 0.75 so you can go ahead and choose one. For example, if you see that age is more important than the distance, then you take age instead of distance in your subsequent analysis. You can write a code that will take out only the variables with correlation less than 0.7. So let's take an example of RAD and tax. So RAD and tax are highly correlated. You can see this is tax and this is RAD. The correlation is 0.91. It is here. The correlation is 0.91 between RAD and tax. So we want to see which one are we going to select to add to our model. So you need to select a variable, one of these highly correlated variables in your model. So in order to determine which one to select, we can fit a crude model, linear model between these two, between the outcome and one of these independent variables. First of all, you can look at the p-value, but as you can see, both of them are statistically significant. So then we can go ahead and look for which one has a higher predictive performance. For linear regression, we look at the multiple R squared. So the multiple R squared is the percentage of which the variable explains the variance in the outcome. So the higher the R squared, the higher, the bigger the predictive performance of this variable. So for RAD, we can see RAD gives us 14.56% multiple R square. The adjusted R square is when you have other features. The change in the adjusted R square tells you how the model how the model performance changes when you add more features. So for this case, we are taking the multiple R square. So while for tax, it is 21.95%. So you see that the variable tax has a higher predictive performance than RAD. So if you want to choose between these two variables that are highly correlated, I would go with tax. So that's one way to determine which variable you're going to choose. So yeah, let's first fit a linear regression model. So we are going to fit this linear model, but we are going to fit a simple linear model of the outcome and one dependent variable, which is L stats. L stats, we said it is the lower status of the population in percentage. So when we run this, we get the fit, which is this first model that we get. L stat, we see the estimate is negative 0.95, and the p-value is statistically significant. The R square is 54.4%, and we can interpret this as for every increase in the percentage of L stat, there is a 95% reduction in the outcome, which is the mean value of the owner-occupied homes in thousands of dollars. So let's plot this second code. This other code is for we plot. We add the AB line is the regression line, and we color it red. So by adding the regression line, this is how it looks like, the plot of MED-V versus L stat. So yeah, that's the crude, like I'll call it the crude linear model for one feature. So we can get other components of this model, and we see what this model is what this fit has. So it has coefficients, residuals, effects, confidence intervals, blah blah blah. So if we want confidence interval, we run this model conf_int and we put the fit, and it gives us the confidence intervals for the estimate. And we see it is between negative 1.02 and negative 0.8, and it is within statistically significant still, because it is in one direction. This is a linear regression, so it is the signs that matter now, the direction. So let's now look at the assumptions of this linear model. So if we are going to do linear regression like we looked at last time in our theory, so first we want to see because we want to look at the assumptions of existence. We want to look at the assumptions of linearity, the assumptions of normality, and homoscedasticity and independence. So just by running this this plot, you can get all the diagnostics of this model that you want. This first if I remove this hashtag, the first line of code, it allows you to plot all the plots on one plot like this. So, but if they are now small, if you can't see them well, you can plot them one by one. That's why I had put a hash to it. So that's why that's how I can get one plot at a time. So the plot of residuals versus we shall start from the plot of residuals versus the fitted values. So this plot checks for nonlinearity or unequal error variance. So so as you can see, it has to be this dotted black line. That's the ideal. So while for this we see like it is like a curve. So this doesn't show a linear relationship between the outcome and the predictor. So it means we have to do something about it, as we shall see. When we plot the normal choo-choo plot, or the choo-choo plot for the residuals, or the standardized residuals versus the theoretical quantiles, so this checks to assess whether the residuals are normally distributed. So it is the normality test is for the normality of the residuals, not the normality of the independent variable or the outcome. So this should be as straight as possible, but you can see it bends off, so this is not normally distributed. So the scale location, this is the spread location plot. In other words, the square root of the absolute standardized residuals versus the fitted values. So this one checks for homoscedasticity, all equal variance. So it takes into assumption that the variance is constant for the constant variance of the residuals, and it's not supposed to show any pattern, or it's supposed to be a straight line through one. So but we can see that this is like a curve which indicates that there is increasing variance as fitted values increase. So the last test is the residual versus leverage. This is a test for outliers. So the test for these outliers, or the outliers that have influential or the influential points that affect the model. So these are the outliers that affect the linear model or the regression analysis. So as you can see, the dotted line is the Cook's distance, and we see that we have outliers at 2.15413 and 375. These ones greatly affect the regression line, and they have to be checked out. So that's how you do all the tests for assumptions of a linear regression with one command. You just plot the fit of the linear regression. Or you can do it one by one. For example, you can start off by assumptions of existence or a linear relationship. So this assumption of a linear relationship is you plot you get a correlation plot and add a regression line. So this is, as you can see, that this, as we say, that this has like a curved pattern, which is not a linear relationship. This violates, this assumption is violated. So the assumptions of normality of the residuals, so we can do a Shapiro-Wilk test with a null hypothesis that data is not normally distributed, and if we get a significant p-value, we say that data is not normally distributed. We can also check the histograms and the k-density, the choo-choo plot. Let's see. So the Shapiro-Wilk is already telling us that the residuals are not normally distributed. Looking at the histogram, yeah, you can see, yeah, it's not normally distributed. And the QQ plot verifies everything, as we saw up. So the test for homoscedasticity and linear residuals and independence, we're going to do them at the same time because they look similar. As you can see, this has a pattern of the increase in squared absolute residuals versus the fitted ones. They tend to increase as the fitted residuals increase. So for the linearity, as you can see, again, there shouldn't be a pattern, but we can see that again they are increasing. And for this one, this should be within the zero, or within at least it should be centered around zero, but we can see these are the scattered plots which are far from the zero. So what do we do if we see that this variable, remember we have only plotted one value of L star, because if you have linear, we have numerical variables, we need to test for all the assumptions. We have only tested for one, and we have a whole lot to go through, but I won't go through that. I'm just showing you what you're supposed to do. So what do? We can first add a squared term, and we see if this will make our plots better. So if we add a squared term, you see at least this one, the normality, yeah, it tends to be around 1 for most of the time, but it goes off sometimes. The QQ plot becomes better, but again, these points here show that these points need to be checked out. You see now this one shows a pattern. Again, it is these points that are pulling the regression line. Then for the outliers, we can still see them. They are here, here, and here. So what do? We can try a log transformation, and we see if it fits the data better. The log transformation still shows almost the similar patterns. Yeah, so it means we are going to look for these outliers and try to deal with them. There are two ways you can deal with these outliers. You can delete them if you have if your data is large enough, the sample size. or you can go back into your case report forms and check for the correct values and check if there wasn't a data entry error. Or you can use other methods which are like the robust robust linear regression analysis. But we're not going to do that. If you use robust linear regression analysis, you don't need to worry about these outliers. There is a way the regression analysis is not affected by these outliers. So let's plot the histogram and the box plots, and we'll look at these outliers. So when you look at the box plots for all these numerical variables, you can see that they are all in their own shapes. And when you look at the box plots, although I've plotted them all in one, because of this command that says for every numerical variable, get for me for every I in the column of numerical variable, plot a box plot of I of that variable, and so on. So, but you can see, like for this ZN, there are several up. At least this one is okay. For L start, we can see they are up here. Again, we can delete this, but we're not good. I've told you what to do when you get these when you come across these outliers. You can either delete them, you can check for them, or you can use the robust regression analysis. So yeah, we are not going to do any of that. We are going to proceed. I'm just illustrating to you what should be done. So we could delete them, and we see that if the model really changes, you can do that in your own free time. So now let's predict the model. Let's predict a model where the L start is 5%, 10%, and 15%. So we use the fit that we have, and yeah, we get our predicted values. So we predict that the MED-V, the median value of owner-occupied homes in thousands of dollars, will be 29, 25, and 20 when L start is 5%, 10%, and 15%. And these are the confidence intervals. So this is how we use the linear regression to predict the outcome. So this is how we use it. So now let's do a multiple linear regression. The multiple linear regression, that's when we add more predictors or more more features or more independent variables. So for this case, for fit 2, we are going to add only age, and for fit 3, we are going to add all the variables. So adding all the variables, we just need this small command, outcome (dot, data), and you choose the data. You realize for these first models, we don't have the the command where we say that data equals Boston, because we attached Boston. We don't need to have it, but you can have it if you didn't use the attach command. So the first, while with L start and age, you can see they are both statistically significant. You see L start changes now to negative 1.03, and so on and so forth. The multiple linear regression is 55%, and the adjusted R square is 54.95%. While if we add all the variables, we can see that the adjusted R square changes to 73%, meaning the 73% of the variance in the outcome. This is like the change in in the predictive performance of this model. While the multiple R-squared says the 74% of the variance in the outcome is explained by these features that we used. But we can see there are some features which are not significant, like this one. Now age is not significant either. So this takes us to, we could do model diagnostic again, and we see, yeah, it improves, but not so much. So let's do now selection of variables to include in the main model, and we see how to take out these non-significant variables. There are two ways. We can use either the stepwise method. You can use the backward as one of the method, or the forward. So the backward, it means you start with a full model like this one, and you remove one by one feature at a time, those starting with the one with the highest p-value. For this case, we would remove age first. But we have a command for that, and it's called the step. We can run a step command, and we see. So if you don't specify the step command, it will use the direction as backward. It will start with the full model. So starting with the full model, it determines the AIC and BIC, how the model is performing. By removing age, it goes ahead. Then step 2, it does this. So it shows you how it came out with the results. And you see the rest of the model, the rest of the variables that remain in the model are statistically significant. The multiple R-squared doesn't change, and the adjusted R-squared doesn't change that much. Meaning those two variables, even if they were within the variable within the model being removed, the predictive performance doesn't change that much. So we can use also stepwise selection, the second method, where we use the direction as forward. Meaning we start with an empty model, and we add only a significant variable to the model according to AIC and BIC. That's what this does. So let's run it, and we see. So as you can see, it started with a full model. It hasn't shown us the steps. It has just run all the model at once. Yeah. Okay. Now let's see. Yeah, it hasn't really done much. So that's why starting off with an empty model is not a good thing. So starting off with a full model and do a backward selection does much better. So if you want to do this manually, you can just use the update function. So for example, our fit 3, this one, which one is it? This one? Yeah, fit 3. Yeah, fit 3 had the full model. You can remove age, which is with a high p-value, and index by just updating the model. And we say fit 4 is going to be the update of fit 3. Take all variables except age and this. Then we run the summary, and we see we come to the same conclusion. Yeah. So you can also do this manually. This is now the manual selection of the step or the backward elimination method. Then we can use this package if you want to set your p-value or the threshold p-value. Normally we set a threshold p-value at bivariate such that you give lenience at bivariate for any interaction or confounding that might have happened. For example, if we start with a full model, we can perform the backward elimination by stating OLS, the ordinal least square method, step backward, that's the command. Or this would be, okay, let me skip that. This is the command. Then you fit this full, you include this full model, and you put a threshold p-value which is 0.2. Let's see what it gives us. So this is what it gives us. This is the summary of the, it has removed these two because of the AIC, and it shows you how the adjusted the R square and adjusted the R square changes. So this is the summary of the final model, and it gives you the final model with the significance, the lower confidence interval, and the upper confidence interval. So we get the same answer, but here we set our threshold. So we get the same answer because this edge and index really had high p-values to begin with. So there is no way they would stay in the model. So we could go ahead and assess for nonlinear relationships, like assessing for interaction. So if you want to assess for interaction, you write the interaction term is supposed to be you add a multiple, or this the multiplication sign in the code. So by running that, it gives you the two variables and the interaction term, which is this one. So interaction term is significant. It means both variables that make up the interaction term must stay in the model. That's what it means. And the adjusted R square and the R square, it gives you that. So we can also assess for quadratic relationships. This is the quadratic term. You put this I because if you don't, the model won't know that, won't differentiate that you are squaring a variable. So you need to include it. So you can see the quadratic term is significant, and this. So we can plot this and we see how it looks like. You see that really the quadratic term fits our data appropriately. So if we add a polynomial term, maybe we could see how this changes. So you can see that now the quadratic term and the other linear, just the linear model, things are different now. If we add the AB line, you would see that it would be crossing maybe here, where this quadratic term fits the data more. And I'm sure if you run let's plot this and we see. Let's plot fit 6 and we see. Yeah, they try to. Yeah, you can see this is quite closer to 0. The QQ plot is better, but still there are these outliers, and these are the outliers that are shifting the regression line. Yeah, but still, if we add a polynomial term of degree 4, this is how you add a polynomial term of degree 4 of all any degree. you specify with the poly as a polynomial term. So yeah, let's do that and we see. So the first red line is our quadratic, and the blue one is the polynomial. You can see fit 7 is the blue one with the polynomial term. And you can see that it is trying to maneuver around the data, and this causes overfitting of the data. So we can't use a polynomial of fourth degree. It overfits the data. It tries to fit every point. You see, it tries even to get this outlier point. That is the dotted line in blue. While our fit 6 was the quadratic term, and in red, you see that it clearly fits our data well. So yeah, so there are different shapes we can use for these lines, and these are the shapes. You can just change the cyc. It's called the cyc. 20 is the, I think it's the dot. We can use 18 and we see. We can use 18 here and we see. Oh, come on. Okay. Yeah, so 18, yeah, these rectangular ones. Yeah, so that's just a by the way to show you the dots that are there. So if we want to write a linear function, this is also a by the way. So if you want to write a linear function, you can write it that the function takes in the values of x and y, and you fit a linear model of y on x, plot x and y, and add the linear, the regression line. So that's a function. So if you want to use the function, you can just use it. I called it linear model.fit. You can use this function of linear model.fit and add these two. This is x first and y second. So the function takes in x and y. If it was taking in y and x, I would switch these positions. So yeah, it gives you the same results as you can see. The second plot, this is the linear function. If you want to change something in your, add labels in your function. So that's why we leave these 3 dotted lines, and the dotted line is here, so to make sure that you can add more terms when you are using the function. So when you're using the function, these dotted lines enable you to add all these other things like the labels, the what, because you specified. You can even change the color, things like that. Yeah. So that was all for linear regression. The next phase we are going to look at logistic regression, and we shall be using another data set, and we shall also be looking at the linear discriminant analysis, all the LDA, and we see the differences between the linear model, linear discriminant analysis, and the logistic regression. And yeah, so thanks for watching. Please remember to subscribe to our channels, and push the like button, comment. Thank you very much.